Thanks a lot, Morali. So I'm Chad Martin. I lead sales for Graphcore North America, and I'll be going through the first hardware section. So as I said, I'll walk through the hardware and echo Morali's comments, either verbally or in chat. Let us know questions when you have them. No need to save them for any particular point, and we'll try and hit everything that's of interest. So to jump into things here. So first off, Graphcore has an entire solution. There's a chip that's the base of it, but really that has to be paired with software so you can interact with it, and then entire platforms, really how it's sold. So you can't just go buy a chip or a card and have it work. You really have to buy the entire platform together in order for it to function. Morali mentioned that Argonne has a BowPod64. I'll show what that means in a little bit compared to some other systems that are available, system sizes. But that's how we look at the total set of platform. But I'll start today with start at the chip level architecture and then show how that scales up to bigger and bigger platforms. And then we'll go into how that morphs for the exact current solution that's there today. So first off, I think it's always important to baseline versus what people are familiar with. And we're familiar with CPUs and GPUs, and our IPU, or intelligence processing unit, does some things a little bit differently than those. So a CPU, for example, is primarily designed for scalar processing. They've obviously added SIMD engines over the years to have some amount of vector capability, but it's not their core strength, which is then the reason why GPUs exist. Now, CPUs also, they'll have caches to try and improve memory latency and reduce some of the bandwidth needs, but their primary memory is these days the DDR-based external that has a high capacity, but is pretty slow. Is there a question here? Okay, small. Now, when you go to the GPU side, there are essentially a lot of SIMD or single instruction, multiple data, or single instruction, multiple thread architectures that were originally designed for graphics, but because they do a lot of vector calculations in parallel, were really well suited for AI as well. They mostly just added matrix engines to that. And a big difference, besides just that compute portion for GPUs, is they had faster memory access than the CPU. That started out with some of the same DDR at the beginning, then they got the GDDR, and then HBM is state of the art these days. So that has a little bit of a different trade-off versus DRAM and a CPU. It reduces the capacity and dramatically increases the bandwidth. With IPUs, we went a step further than that in both the compute and the memory standpoint. One of the biggest challenges in compute is both the latency and power draw of moving data back and forth. So each of our cores on the chip have local memory that they access. So therefore they, and that local memory is SRAM. So it's dramatically faster than what you can get with off-chip memory, and then has lower power since you're not moving it back and forth as much. Because of that, we don't have caches in the same sense of other architectures today. I'll explain a little more later why that is beyond just the close memory. But as you can see at the bottom, there's a dramatically bigger amount of memory bandwidth possible by using all SRAM than going to HBM. And I know this is a A100 example. Those numbers have gone up with current, but it still gives the same range. Maybe it's a 4 terabyte per second. There's some announced ones that go up in the higher single digits, but that's still dramatically lower than what you can do with all SRAM. Of course, like the trade-off going from a CPU memory pool to a GPU with HBM, the trade-off for all that bandwidth is capacity. Now, looking at how the architecture works is we use a technique called bulk synchronous parallel, which was invented prior to IPUs, but it was more meant for HPC systems and was a software level implementation to make it easier to program to large parallel systems. The IPU is an implementation of bulk synchronous parallel in hardware rather than software. Now, you saw on that last slide, there were a ton of cores with individual memory, and that's part of the reason why doing a process like this works, because you hear about in CPUs these days, 64 cores, starting to go up to 128 and even beyond. But we have 1,472 cores, each of those having 6 threads. And so that is a lot to manage if it's just like a round robin, everything working independently. Bulk synchronous parallel gives a way for the compiler to map all that out ahead of time. And since we're only doing AI and can do other stuff, but we're only focused on AI, and the programs get compiled on the CPU ahead of time before they run on the IPU, we have the luxury of planning that out and not needing to have the random processes and branches and everything that a CPU has to deal with. So basically what's BSP solved is you don't have that concurrency because it's a little more predictable. It is efficient for lots of parallelization. And then our SDK that I'd mentioned as part of the software solution essentially enables that you don't have, as a programmer, have to be aware that this is a BSP architecture. You'll go into something like PyTorch and create your model just like you would for any other architecture. And the compiler knows what's going on underneath and is able to efficiently optimize. Now, what that looks like when you start to scale out across devices is that same process that allows us to go to almost 1,500 cores and over 8,800 threads also allows us to scale to multiple devices as well. So this example here was 64 devices, which is what the Argonne system has if it's being fully utilized by one model, and 64 chips. And each of those has an exchange. So actually, I missed one thing here. Part of the process here is there's a compute and sync and exchange process here that's shown over on the right. And the exchange is done through all the links between the chips, what we call our IPU link that directly attaches them. So it's not going back to the host CPU for any of that exchange. It's all through that dedicated connection. And so that all gets mapped out ahead of time when you're doing the compilation, and if you're selecting that you're using 64 IPUs rather than one or some number in between, the software will plan out what gets done on which device. Now, that then can scale further to across systems. So if you want to take multiple POD64s and have them operate as a single system, a pod 256, for example, which would be 4 of these, as you see in this diagram, the IPU links are also capable of going between racks and connecting further. So there's quite a bit of scalability that's possible with this system as it's architected. Now, looking at the individual products, the current design that we have is based on the Bow IPU, and that was a enhancement to our previous generation chip that added something called wafer-on-wafer technology, which we worked along with TSMC for them to produce. And it exactly what it sounds like. You take 2 logic wafers, or 1 logic wafer, 1 power delivery wafer, and you put those together. And that enabled us to, with the same amount of transistors, increase the clock frequency by about 40% while staying in a similar power range. So it was a very effective way to improve capability, and especially for a large design that is very repetitive with all the cores being identical, it works really well. So as you can see, I mentioned some of these numbers before. There's the 1472 independent tiles. Each of those has their own memory. So we'll list that there's about 900 megabytes of in-processor memory, meaning SRAM, which you can see down at the bottom here. But it's not like this big pool of 900 megabytes. It's each of those cores has its own equal chunk of that it uses. Likewise, the memory bandwidth is when you add up each of the cores and its individual bandwidth to memory, that's what you get. So, but it's very efficient. And then during that exchange phase, when one core finishes and its output is needed by another core, there's an IPU exchange that has 11 terabytes per second of total bandwidth available. So that gives plenty of communication in order for the data to flow within the processor and keep moving. So it's not bounded by external communication. And then we do have a PCI Express connection that ultimately goes to host, but it's a little different in our architecture. I'll show that a little bit on a further slide, how this chip connects up to the host system, because that is also different than what you'll see elsewhere. Okay, don't see any questions yet. Okay, now if you want to look at, there's the chip. Now, what am I actually interacting with if I'm using one of these? And so the basic unit of compute here is this BowPod2000, which is a 1U rack-mounted system that has 4 IPUs. You can they're air-cooled. You can see the 4 heat sinks in the middle. And each of those have the IPU links directly between them, as well as there's IPU links that go outside of the chassis, as you can see here in the bottom right of the picture. And so that's how you connect up one BowPod2000 to another. So it's with these 1U blades. The on chip here, there's a gateway chip. And so the PCI Express that was mentioned coming off the chip actually goes to this gateway. And the host connectivity is actually through 100 gigabit Ethernet rather than PCI Express, like a lot of systems that gives a different kind of flexibility for building the design. Yes, so a good question, Alfred. Besides IPUs, is there a CPU on a node? So at this part right here, the answer is no. I'll show in another slide where the CPU comes into it, because it definitely needs a CPU, but it's not on this BowPod2000. It connects into a standard server. So that's because of how these are connected here. There's not a fixed ratio of CPUs to IPUs like you might find in other systems. It can be a lot more flexible than that. And why you might have different CPU needs depends upon what you're doing. If you're doing, say, models that are computer vision, that have a lot of images to deal with and process, you're probably going to want some more CPU capability than if you're just doing language models that the CPU is much faster at preparing the data for. So I'll show later our recommendations for standard configs, but they can be optimized with different amounts. Then also these IPU, well, I talked about the gateway chip, which is under this heatsink. There are also some IPU gateway links. Sorry, that's right here. And that's how you connect between multiple racks. So the IPU links over here are how all the BowPod2000s connect within a rack. When you're stringing multiple BowPod24s together, you would then use the gateway links to connect rack to rack. Okay, so I think that's probably good on this one. Looking out to how it all connects together. So I mentioned here about the gateway chip and showed it on the other picture. Here's more of the block diagram view. And so that gateway connects out to a NIC, and then that NIC is how the host interconnect work. So you'll have a server, which in the case of the Argon system is a Dell PowerEdge R6525 that has dual 64 core processors in it. And that server connects to a switch via 100 gig Ethernet. Each of these BowPod2000s connect to the same switch via 100 gig Ethernet. And then that's how they communicate with each other. So that's where you can get that flexibility in the number of servers that you need to have in that. Now, most of this I already talked to. There's just some aggregate numbers here. If you look at the flops, just breaking out what an individual chip can do with one of the BowPod2000s, really just multiplying by 4, you get the 1.4 petaflops of FP16 compute. You get the almost 6,000 processor cores and over 35,000 parallel threads. So it's quite a bit there. We do also have on the B2000 some DRAM. It has 128 gigabytes typically configured as DRAM. However, because that DRAM sits behind the gateway chip, it does have limited bandwidth to the Bow IPUs. So it's really meant for saving you from going back to the host system rather than high bandwidth memory to access when performance is really needed. So the system sizes that we have today are the Pod 16, Pod 64, and Pod 256. A Pod 16, you'll have 4 of those BowPod2000s and then 1 server. The Pod 64, you have 16 of those BowPod2000s and between 1 and 4 servers. So that's where that flexibility comes in. Is by default, we recommend 4 servers, but if you know what your workload is and you don't need that many, then you can go with 1 or 2 servers there and limit the server expense. So as you interact with the system, back to the CPU question, you're really interacting with the server. So that's what you're SSHing into. You're running PyTorch on, and that has the SDK, the popular SDK that Graphcore has running on it. And so you do all your work directly there, compile the model, and then that's the point where it then communicates with the IPUs that are on the BowPod2000s and does the external acceleration. And when you have 4 servers versus 1, you're able to spread out the compilation tasks to run faster. So that's one of the big areas for more cores, more CPUs, is just like compiling a typical program on a server takes some time. Compiling a graph to then map to the IPU can take some time as well. So that gets sped up by having more CPUs. And then the Pod 256 is really just taking 4 of those Pod 64 racks and connecting them together via those IPU gateway links that I mentioned. And then you can configure it as a single Pod 256. Now, that doesn't mean that every model needs to use all of those. Take the Pod 64, for example. If you only need 16 IPUs, then you're only going to request access to 16 IPUs, and the scheduler will allocate you the appropriate amount, leaving the rest of it open for other users. Maybe you only need 4 IPUs instead of 16. You can have quite a few simultaneous users if all you're using is 4 of the IPUs. So that's how it gets structured in use. Now, this is just an example of if you look in a little deeper at a direct attach Pod 16. So this is our base config that someone can use. In the Argon situation specifically, since it's a Pod 64, it is not direct attach, it goes through a switch. But if you're doing a Pod 16, it is possible to have enough NICs or it's direct attached. The key there is the host server has to have 400 gig Ethernet ports. And then as you can see over on the left, it has one connection to each of those. And then the IPU links are connected similarly to how you would in a POD64. Now, each of these, obviously, as the point of today's conversation, POD16 usage, POD64 usage is available via the Argonne system. There are also systems available via G-Core's public cloud, if that's of interest as well. Of course, those are paid for and used for other usages beyond just science, like the Argonne system. But that's how this is configured. And then there's also, I didn't talk about it before, but there is a separate management link. And so that POD64 has a separate switch on it. It's really two switches total, 100 gig switch, and then a 1 gig switch for management traffic. Now the POD64, this is what it looks like. So a key difference here, I already mentioned, everything connects up to the host or the switch, and you see here 200 gig connections into the switch from the server. The difference is on the IP links. Instead of them just being connected one-to-one, there is also a loopback at the end that goes from the top to the bottom. So it is that 2D torus topology within a single rack. And then if you're having multiple racks together, it gets more of a 3D torus through those gateway links. And then the numbers over here on the left, just like with the POD16, it's just a flat multiplication for peak theoreticals based on what 64 chips is capable of. So this gives a good overview of how a POD64 is constructed. We only show a single server in this picture, but when there's more, they'll just be stacked on top of here, and then more connections going into each of these top of rack switches. Okay, so that's the end of the hardware portion of the discussion.